Welcome to G Fun Facts Online. In the world of mathematics, the number pi has been a star for nearly 4,000 years. It's the simple ratio of a circle's circumference to its diameter, yet its decimal digits march on into infinity, never repeating. The quest to understand pi is a story of human ingenuity, spanning empires and pushing the boundaries of our knowledge. And just when we thought the story was mostly about mathematicians and supercomputers, a new chapter has been written. Physicists, grappling with the quantum dance of high-energy particles, have stumbled upon a novel and elegant new formula for pi. This isn't just a new curiosity, it's a new tool that helps tackle a modern challenge at the forefront of theoretical physics, connecting a 15th-century Indian mathematician with the bleeding edge of science. Today we're telling the story of this new slice of pi. The earliest known approximations date back to ancient Babylon around 1900 BC, where they used a value of about 3.125 for their engineering and astronomical calculations. The Egyptians, a bit later, used a value of roughly 3.1605. Even the Old Testament gives an implicit value of pi as exactly 3. Describing a circular basin in King Solomon's temple. But the first truly rigorous method came from the legendary Archimedes of Syracuse in the 3rd century BC. Instead of just measuring, he devised a brilliant algorithm. He trapped a circle between two polygons, one inscribed inside and one circumscribed outside. He knew the circle's true circumference had to be somewhere between the perimeters of these two shapes. Starting with a hexagon, he methodically doubled the number of sides up to a 96-sided polygon. Through this painstaking method of exhaustion, he proved that pi was greater than 3 and 10/71 and less than 3 and 1/7. This established a rigorous framework that would dominate the field for over 1,000 years. While Europe entered the Middle Ages, the torch was carried by mathematicians in the East. In 5th century China, the brilliant astronomer Zhu Chongzhi calculated pi to an astounding 7 decimal places, between 3.141596 and 3.141597. It's believed he used a polygon with over 24,000 sides to achieve this, a feat of calculation that's hard to fathom without modern tools. He also gave us the famous approximation 355 divided by 113, which is accurate to 6 decimal places. Then, in the 14th century, a monumental shift occurred in the Kerala school of mathematics in India. A mathematician named Madhava of Sangamagrama moved away from laborious geometry and into the powerful world of infinite series. He discovered that pi could be expressed as the sum of an infinite number of simple fractions. One of his most famous discoveries, now often called the Gregory-Leibniz series, looks like this. Pi divided by 4 equals 1 minus 1/3, plus 1/5, minus 1/7, and so on forever. This was a complete game changer. Madhava knew this particular series converged very slowly, but he even developed correction terms to speed it up, allowing him to calculate pi to at least 11 decimal places, the world record for centuries. The development of calculus in the 17th century by Newton and Leibniz supercharged this approach. Suddenly, infinite series were everywhere, and mathematicians competed to find ever faster formulas. In the 18th century, the great Leonhard Euler made immense contributions. He's the one who popularized using the Greek letter pi, and he discovered dozens of new formulas involving it. He famously solved the Basel problem, showing that 1 plus 1/4 plus 1/9 plus 1/16 and so on equals pi squared divided by 6, a stunning and unexpected link between pi and whole numbers. This brings us to the early 20th century and the enigmatic genius, Srinivasa Ramanujan. A self-taught master from India, Ramanujan had an almost mystical intuition for numbers. He produced extraordinary and rapidly converging series for 1 over pi. One of his formulas from 1910 is so powerful that each new term in the series adds about 8 correct decimal places to the calculation. His formulas were so advanced, they became the foundation for the fastest computer algorithms decades later. The arrival of the electronic computer in the mid-20th century transformed the quest entirely. In 1949, the ENIAC computer calculated 2037 digits in 70 hours. By the 1970s, we knew 1,000,000 digits. Today, using algorithms based on Ramanujan's work, the record stands at over 100 trillion digits, a calculation used to test the limits of modern supercomputers. And then, in 1995, another surprise, the Bailey-Borwein-Plouffe, or BBP formula, was discovered. It wasn't the fastest, but it had a magical property. It allows you to calculate any single digit of pi in base 16 without having to calculate all the digits that come before it. This was thought to be impossible. This long, storied history, from ancient estimates to exotic algorithms, brings us to today, where the latest chapter comes not from a mathematician's study, but from a physicist's blackboard. The newest discovery emerged from the highly complex world of theoretical physics, from the work of Arnab Priyasaha and Aninda Sinha at the Indian Institute of Science. Their goal was not to find a new formula for pi. They were trying to solve a very modern and very difficult problem: how to better describe the way subatomic particles interact at incredibly high energies. At the heart of particle physics is the question of what happens when particles collide. The math describing this process, called a scattering amplitude, is monstrously complex. Physicists are constantly searching for better models, what they call an optimization problem, to make these calculations manageable but still accurate. Saha and Sinha were using tools from string theory, the idea that fundamental particles are tiny vibrating strings. They took an early string theory formula called the Veneziano amplitude, which is expressed using a mathematical tool called the Euler beta function, and tried to combine it with the more traditional language of Feynman diagrams, which are the stick figure drawings physicists use to visualize particle interactions. They were looking for a new, more efficient way to represent these complex quantum interactions. As they worked to build their new model, their equations simplified in a surprising way. And out of the machinery designed to describe the quantum world, a new infinite series for pi simply fell out. As Sinha explained, our efforts initially were never to find a way to look at pi. We were excited when we got a new way to look at it. Even more remarkably, they soon realized their formula had a deep historical connection. In a certain mathematical limit, their 21st century, physics-derived formula transformed into the 15th century formula of Madhava of Sangamagrama. This unexpected bridge, connecting the frontiers of modern physics with a 600-year-old mathematical discovery, was a beautiful and humbling realization. It was as if the fundamental laws of the universe were echoing the insights of a medieval genius. So what does this new formula actually look like? While its full form is complex, its most intriguing feature is the presence of a parameter, which they called lambda. This is a free parameter, meaning you can choose its value, and the formula will still converge to pi. This is highly unusual. The existence of lambda is a direct imprint of the formula's origins in physics. It's a mathematical memory of the simplifications they made in their physical model. This parameter also gives the formula a practical advantage. By tuning the value of lambda, you can change how quickly the series converges to pi. While it's not faster than the algorithms used for record-breaking computations, it can be made to converge much more quickly than the classical Madhava series it's related to. One of the most elegant aspects of the Saha-Sinha formula is this deep connection to Madhava's work. If you take their formula and let the parameter lambda go to infinity, it reduces exactly to Madhava's series. This means the ancient Indian formula is just one special case within a much larger, continuous family of pi formulas that they uncovered. Their formula provides a modern, physics-based framework that encompasses a 600-year-old discovery. It shows how a series that arose from early explorations of calculus in India also naturally emerges from the mathematics of string theory. So when headlines say this new formula helps solve a long-standing problem, it's not referring to an ancient mathematical conjecture. The problem is a fundamental challenge in modern physics. the efficient and accurate representation of particle interactions. Calculating these interactions is computationally brutal. For decades, physicists have been on a quest for better optimization methods, simpler, more efficient models that still capture the essential physics. The work of Saha and Sinha is a significant step forward in this quest. Their new framework for representing scattering amplitudes is a more efficient recipe for describing the physics. The new pi formula is a proof of concept that their method works. It's a mathematical reflection of their new, more efficient way of representing the physics. The method used to derive the pi formula can be applied to the scattering amplitudes themselves, giving physicists a new tool that is more efficient and provides deeper theoretical insight into the models they use. This breakthrough could have ripple effects. One direct application is in studying hadron scattering, the interactions of particles like protons and neutrons. The researchers suggest their new representations could be used to re-examine experimental data from particle accelerators, like the Large Hadron Collider, potentially leading to a more refined understanding of the strong nuclear force. An even more speculative application is in a field called celestial holography. This is an ambitious research program that aims to unite quantum mechanics and general relativity. The idea is that our 4D universe could be a hologram projected from a 2D surface at the edge of the cosmos. Saha and Sinha's work, by providing a new way to organize scattering amplitudes, might offer a new language to help build the dictionary that translates between the physics of gravity and the physics of the hologram. Beyond specific applications, the formula opens up a new playground for theory. The existence of a free parameter in a formula for a fundamental constant like pi is a novelty that will surely inspire more research. The story of pi is a mirror of our own intellectual journey. This latest chapter, written by physicists, beautifully encapsulates the interconnectedness of scientific knowledge. A problem at the forefront of 21st century physics led to a new representation of a 4,000-year-old number, which in turn reached back across centuries to find a kinship with a 15th century mathematical pioneer. This new slice of pie doesn't just give us more digits, it gives us a new tool and a new language for describing the fundamental workings of our universe. It is a powerful and elegant testament to the fact that the deepest truths of mathematics and physics are intertwined, and that profound discoveries can emerge from the curiosity-driven exploration of the unknown. The journey of pi is far from over. Thank you for listening to G Fun Facts Online.